In this series, we will look at the neural network models that do not use the backpropagation algorithm. In this video, we'll look at the Hebbian learning model as our first model. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. Let's take a look at the full table of contents for this series. In Chapter 1, we'll look at Hebbian learning. We'll look at Hebb's learning rule and use it to perform simple pattern recognition. Next, we will look at how to apply weight decay in Hebbian learning and use it to classify MNIST images. Although the MNIST classification performance is not as good as the backpropagation algorithm, it helps us better understand how Hebbian learning works. In Chapter 2, we will look at the Hopfield network, which can be used for associative memory, etc. In Chapter 3, we will look at a Boltzmann machine and a restricted Boltzmann machine. In Chapter 4, we will look at contrastive Hebbian learning, a variant of Hebbian learning. We will use this to improve the performance of the MNIST image classification task we performed in Chapter 2. In Chapter 5, we will look at another variant of Hebbian learning, the competitive model. We will use this to perform clustering tasks. Finally, let's look at the self-organizing map, SOM, also commonly known as the Kohonen network. In the first video of the Deep Learning course, we looked at a brief history of artificial neural networks as follows. So far, we have looked at deep learning models based on the perceptron and backpropagation algorithm proposed by Frank Rosenblatt and David Rumelhart. The RNN, CNN, autoencoder, and GAN models we've looked at so far all learn model parameters by backpropagating the gradients of the loss function. And these are all types of supervised learning. In this series, we will look at Hebb's learning rule and its variants that can be used for both supervised and unsupervised learning. In fact, the development of the backpropagation algorithm has dramatically improved the performance of deep learning models. Additionally, deep learning enables high-level abstraction of data by using architectures composed of multiple nonlinear transformations. These deep learning models require very large amounts of labeled training data. Our brain, however, seems to be able to solve problems using less data and fewer layers. Perhaps the backpropagation learning rule, the use of many layers, and the use of huge amounts of data are a departure from brain-related principles. In this context, understanding Hebbian-related learning rules that do not use backpropagation can help us understand how our brain works. Now, let's look at what the Hebbian learning rule is. The Hebbian learning rule, or simply Hebb's rule, was introduced by Donald Hebb in his 1949 book, The Organization of Behavior. This rule is often summarized as neurons that fire together, wire together. Donald Hebb states it as follows. When one cell repeatedly assists in firing another, the axon of the first cell develops synaptic knobs or enlarges them if they already exist in contact with the soma of the second cell. This means that the synaptic strength between two neurons tends to get strengthened whenever the two neurons both fire. Let's take this neural network as an example. The structure of the network is identical to a typical feed-forward network. There is an input layer and an output layer, and the connection weights are fully connected. The output of the network is computed in the same way as a feed-forward network, as follows. F is the activation function for the output layer. The weights are updated as follows. This is the simple Hebb's learning rule. Instead of using gradient descent, W is updated by multiplying the activations of the input layer by the activations of the output layer. Alpha is the learning rate. If both x and y are 1, W increases by alpha. However, if either x or y is 0, W is not updated. This is what is meant by neurons that fire together, wire together. If the activations of the input layer are 0, 1, 0, 0, and the activations of the output layer are 0, 1, 0, then these two neurons are activated. So this connection weight value increases. Other weights are not updated. Delta U can be simply written as follows. The output layer may have bias added, like a feed-forward network. Next, let's perform a simple pattern recognition task using Hebb's learning rule. We have these two simple images. We want to use the Hebb's rule to create a neural network that remembers and recalls these images. The first image represents the letter T, and the second image represents the letter U. The pixel values in the images are either +1 or -1. +1 is the foreground color, -1 is the background color. This image is represented as a one-dimensional vector, like this. The neural network is structured as follows. There are 9 neurons in the input layer and 1 neuron in the output layer. And there's one bias. This is a typical network for binary classification. The image vector X represents the activation values of the input layer neurons. A +1 means the neuron is activated, and a -1 means the neuron is not activated. The activation value of the output layer neuron is either +1 or -1. Let's say that +1 represents the letter T, and -1 represents the letter U. Initialize both the connection weights W and the bias B to 0. Hebb's learning rules are as follows. Let's set the learning rate alpha to 1.0. The activation value of the bias neuron is always 1. That is, the bias neuron always fires. So the bias is updated like this. In the first step of the training stage, the first image is input to the neural network. Using this formula is updated as follows. Initially, all elements of W are 0, and each element increases by the product of X and Y. The bias increases from 0 to 1. In the second step of the training stage, the second image is input to the neural network. Then W and B are updated as follows. Now both images are remembered by the neural network. Next, let's recall the pattern stored in the neural network. This is identical to the prediction process in a typical feed-forward network. Let's input this image into the neural network. If we use this formula to calculate the y value, we get 1.0. The hyperbolic tangent function was used as the activation function. A positive 1 represents the letter T. Therefore, this image is recognized as the letter T. When we feed this image to the network, we get a y value of negative 1.0. Therefore, this image is recognized as the letter U. This time, let's input partially corrupted images into the neural network. The output of the neural network for this image is a positive 1.0, so it is recognized as the letter T. This image is recognized as the letter U. This shows that this network is good at recognizing even partially corrupted images. Next, let's create a neural network that can recognize multiple characters. This corresponds to multiclass classification. Let's store these 3 patterns in a neural network. This time, let's set the foreground color to 1 and the background color to 0. You can also set them to positive 1 and negative 1, as in the previous example. The structure of the network is as follows. The input vector x for each pattern is as follows. The output vector y is 1-hot encoded as follows. The output layer has 3 neurons. The bias is omitted for simplicity. The weights are a matrix with 9 rows and 3 columns. The initial value of each element is 0. Let's feed the first pattern into the network. We use this formula to update the 9 weights connected to the first output neuron. Then the first column vector of the weight matrix is updated as follows. We update the second and third column vectors of the weight matrix in the same way. Since the y values of the first pattern are 1, 0, 0, only the first neuron should be activated. Therefore, only the first column vector of the weight matrix is updated, and the rest are not updated. When we input the first pattern, the weight matrix is updated as follows. As the iterations progress, the weights tend to increase. To prevent this, we can normalize the weights at each step. Next, we feed the second pattern into the network, updating the weights in the same way as on the previous page. Since the y values in this pattern are 0, 1, 0, only the second neuron in the output layer should be activated. Therefore, only the second column vector of the weight matrix is updated, and the rest retain their existing values. The weights are updated as follows. Finally, we input the third pattern into the network to update the weights. The weights are finally updated as follows. Next, let's input the partially corrupted pattern into the trained neural network. When we input the vector x into the neural network, we get the following outputs. we use the softmax as the activation function. We can see that the first neuron in the output layer is most likely to be activated. So this pattern is most likely the letter T. For the second pattern, the third neuron is most likely to be activated, so it is recognized as the letter C. The third pattern is recognized as the letter U. Finally, let's implement this example in code. The input data X is as follows, and the output data Y is as follows. Initialize the weights to 0. Set the learning rate alpha to 0.1. Update the weights for each input pattern. And then we normalize the weights. Repeat this process 100 times. The updated weights are as follows. Next, let's input 3 partially corrupted patterns into the network. The output of the network for each pattern is as follows. When the first pattern is input, the first neuron in the output layer is activated. When the second pattern is input, the third neuron is activated. And when the third pattern is input, the second neuron is activated. Therefore, the first pattern is recognized as the letter T. The second pattern is recognized as the letter C. And the third pattern is recognized as the letter U. Let's run this code. We got the following results. So far, we have looked at the simple Hebb's learning rule. In the next video, we'll look at Hebb's learning rule with weight decay.